My name is Kevin Farley. I'm with the SQL Server team. My colleague Sunil Agarwal is here as well. And we're going to talk about operational analytics. So how many of you guys have used operational analytics? How many of you guys know what operational analytics is? Okay, good. How many of you guys have used column stores? More, that's good. That's about a quarter. How many of you know what column stores are and how they work? That's most of you, majority. Okay, that's what we're here to fix. That's what we're here to make sure that when you walk out of this room, you understand what these concepts are, what operational analytics is, and when you would use it, when you wouldn't use it, and what it'll do for you. One other term is, you'll hear is HTAP. Anybody familiar with HTAP? HTAP? So that's a term that's coming more in use in the industry. I think Gartner coined it. It's operational analytics. It's just another name. It's starting to be used more commonly, so we'll use those both kind of interchangeably. So we're going to talk about motivation. Why would you do this? What's the problem we're trying to solve? There's no point adopting technology if it's not doing something for you. So what problem are we trying to solve here? We're going to talk about real-time analytics with disk-based tables, traditional disk-based tables, and also with in-memory tables. So this is all about analytics, right? So we're going to talk about what is the traditional analytics architecture. So you have a system that's generating operational data. So in this case, it's an order system. Someone is tracking sales of flowers. So they're just inserting into the transactions, UPC code, flowers, $20 worth of flowers. Obviously, in real life, there would be a lot more data that went with that. But this is, for an example, we're tracking sales of flowers. And it goes through the presentation layer, and it gets kept in your operational database. At some frequency, hours, days, weeks, whatever is set up at your business, you do an extract, transform, load, ETL process across to a database that's specifically used for your analytics. It's another relational database. You run BI analytics on that, get your dashboards, your reporting, so you know how much you're making from selling flowers and what stores do best and all that good stuff. So that's where you get your analytics from. You may insert SQL Server analysis services if you're doing more complex analytics on the data than what is readily doable in native SQL Server. But this is a really common analytics architecture. Probably anybody that does analytics in this room is familiar with it. So what's the problem? It's what everybody uses, right? Can't go wrong. Well, there's some issues here. There's a lot of moving pieces, right? You've got two different databases holding not only the same data, you've got a whole ETL process that you have to keep running and in sync where you're moving data from place to place. That's usually a scheduled job, so you have to make sure it runs on time and doesn't error out, that it cleans up after itself and picks up where it left off. All those things have to be done. That's what you guys are doing today. I'm not saying it's exotic, I'm just saying it's more moving pieces, more complexity into the system. Requires an extra server typically. Most people aren't using the same server for their analytics and their operational store. Data latency in analytics is the one that resonates with the most customers on this. So what do I mean by that? Well, when you're running your analytics, you're running on the data that's in your analytics database, right? The data got there through the ETL process. The ETL process only runs so often. Whether that's hourly, daily, weekly, whatever it is, it only runs that often, which means that the data that you're doing analytics on is hours, days, weeks old. Okay, for some things that doesn't matter. You're looking for long-range trends, and that's okay. But if you're selling flowers, and you want to track which stores are selling flowers the quickest, and which stores may have excess inventory, you'd like to know before the end of the day if the flowers are all going to go bad, and if there's another store that is in a location where they're just selling like hotcakes and they're running out, you'd like to shuffle some flowers from place to place. That'd be a really useful thing to be able to know, but you're not going to find it in your analytics system because it hasn't done the ETL cycle yet. So there's a lot of situations like that where having more timely analytic data can save you money and make you more money. More businesses all the time are demanding real-time data for their analytics. So this is all about minimizing data latency for analytics. That's what we're here to talk about. What can we do to minimize that latency? So again, we have the same system that's generating our data, same operational store. We make a change. We introduce a column store index onto your operational data store, right? Operational data, your OLTP workload goes on unchanged. It hasn't changed at all. But now you can, using the column store index, is really efficient at scanning millions and billions of rows of data. So now you can rationally do analytic queries against that operational database. You can run analysis services in tabular mode against it as well. So what does that get you? That's real-time analytics. That's what we're talking about. We're talking about doing analytics against your real-time operational data store. That's what operational analytics, real-time analytics, HTAP, those are all synonyms for this. Not having that delay, not having two separate implementations, not having an ETL cycle, just up-to-the-minute data. So what are the benefits? Why would you do this? Well, no data latency is a big one, right? If you're doing analytics against the same table that is taking in your operational data, it is by definition up to the second. There is no more up-to-date source of data than that. You don't have to keep up with the ETL jobs. You don't have to make sure all the care and feeding that goes into making sure your jobs always run and they didn't error out and they didn't run out of space. Gone. You don't have a separate system to maintain for your data warehouse. There are some challenges. It doesn't come for free. Nothing does, right? Challenges are in, okay, how do you do all this without tanking performance on your OLTP system? Because that's the one the boss is going to scream at you for, right? So that's a challenge, and we've spent a lot of time working on that and addressing that. And delivering performant analytics. Both sides have to perform well, otherwise there's no gain here, right? This is not a cure-all. There's no magic go fast button in the database world. There's no one solution that fits every problem. It's no different. So if you have multiple different transaction processing systems feeding one repository and you want to analyze data across all of them, that's not going to work here. You can do some analytics on each of your OLTP systems to get spot data that may be local to that system, and then roll them up into an aggregate view for further processing down the line. That may be something that is attractive as well. But a real-time analytics is not going to roll up data from multiple different sources. Extreme analytics, this is just, there are some levels of analytics where you really want to build a cube to get any kind of reasonable performance. This is not doing away with analysis services, it's not doing away with cubes, but for those queries, those analytics that can be solved with a column store, which is an extremely fast way of doing this processing outside of a queue, sometimes it can work. There's challenges with an OLTP schema when you're doing reporting. Most reporting is not looking for highly normalized data, which it would be typically in your OLTP schema. So there's some trade-offs there. There's some give and take you'll have to figure out. So let's dive into real-time analytics in disk-based tables. Before I do, are there any questions about the overall concept, what we're trying to accomplish, what I'm saying that I think we can do? Okay, must be clear. So the first technique we're going to talk about is non-clustered column store index. So most of the room has heard of and or used column store indexes. So in this case, we've got a B-tree index over a standard row store, standard relational table. This is what's in your OLTP system today. Now we add in column stores. What's unique about column stores is that the data is organized column by column rather than row by row. Traditional tables, you have database pages. Each page has a number of rows. Each of those rows has all the columns in that table, right? That's how databases have been organized forever. This breaks that mold and takes a set of rows. Default is about 1 million. There's reasons it can be shorter than that. But say, give or take 1 million rows, and for each column, we'll compress it and put it in its own container. It doesn't live in pages. It's in its own object pool. But we compress all the data row by row. For the kind of data that you're typically going to do analytics on, that's going to be integers and floats, those numeric sorts of data. And all the data in one column is going to be in the same data domain. So it's the same data relating to the same real-time, real-life object. So it's going to compress really well because there's going to be a lot of common values, right? If you're doing a foreign key to a set of 5 values, then those million rows is going to collapse into 5 values when you compress it. So you can get huge compression that way. 90% compression is not untypical. So the way this works is that new data, I said that we compress them into million row groups. Each row group is made of the column segments. So as you add more data into this table, you're not going to compress it one row by one row. We have delta row groups, which are used to collect rows until we've got enough for it to make sense to compress it into another row group. So new data lands in the delta row group, compress it when it's time. That's the workflow. Because these row groups are highly compressed and there's some sorting and reordering, they're not ordered by any given key. Deleting a row out of the middle of those wouldn't make sense. It would be a huge amount of churn. So what we do is we have a delete bitmap. And the delete bitmap, we set a bit for each row that we have deleted, and at scan time, we'll logically just skip that row. And over time, that's one of the standard index maintenance tasks. With a column store, you do a reorganize to collapse that empty space. This is a non-clustered column store index, which means it's not the primary copy of the data. The primary copy is the row store that was in your database to start with. We're just adding this as an extra index that will do very fast analytics. When we delete the data, when you're doing a scan against a row store, you need to find the rows that were deleted very efficiently. And since the row segments are not ordered by key, what we do is we have a separate buffer, the delete buffer, where we keep the primary keys of the rows that have been deleted. It's very fast to find them that way rather than having to do a full scan of all the column store to find the rows that were deleted. So that's what that piece is, and that's how we deal with some of the churn of updating that in real time. So if you look at this overall structure, then if you're adding a new row, you add it into the row store, and you add it into any other non-clustered indexes, the columns that are included in that non-clustered index, and you also add it into the delta row group. Not a whole lot of extra overhead there. Updating a column store is a delete insert. So we mark that row deleted in the delete bitmap or just delete it out of the delta row group and then do another insert of the new values. So the key points here, we're creating an updatable non-clustered column store index for analytics queries. And that means if you've got a table that has a bunch of indexes whose purpose is facilitating analytic-style queries on this row store, you can probably drop them. That reduces the index maintenance work that the system has to do to keep those other indexes up to date. Since the column store will satisfy most of the analytics queries, you don't need them. The optimizer wouldn't choose to use them because it's got a more efficient option now. And so that's one mitigation to get rid of some of the extra overhead of updating a table that has a non-clustered column store. No OLTP application changes. You're not changing your application at all. Just like you don't have to change your application if you add any other kind of index. This is just another index for your application. The B-tree index and the column store data is kept in sync just like the clustered index and non-clustered indexes are kept in sync. It just happens. Part of the consistency model of the database. And Query Optimizer will choose whatever index best fits the job like it always has. It's now just got another tool in its tool chest. So we need to minimize overhead, right? We're adding this whole new structure in here, and we need to minimize the overhead involved in it. So there's a number of operations that might induce overhead to us. We have inserts. In the B tree, you just insert the row into the B tree. Non-clustered column store index, you insert the row into the B tree of the Delta store. Delete. In a B tree, you seek to the row that's going to be deleted, and you delete the row out of the page. Non-clustered column store index, you seek to the row in the Delta stores, and there may be more than one. If you find the row, then you delete it. Otherwise, you insert the key into the delete row buffer. Update, again, for standard B trees, you seek to the row and you update it in place. For non-clustered column store indexes, you delete the row with the steps up above, and then you insert the updated row into the Delta store. So there's some extra work over there on the right-hand side. What can we do about that? Again, there can be multiple Delta stores. If you're doing a parallel load, rather than serializing it into one Delta store, we'll create multiple Delta row groups and go and insert data into them in parallel. So insertion, we used to make the Delta stores page compressed to save space. But what we found is that by design, the Delta stores are highly churn. They have a high churn rate because you're putting new rows into them and then clearing them out to compress them into row groups where they stay for a long time. So any space savings is very transient, but you're constantly taking the hit of recompressing all that data. So it's just not a win. So by turning off page compression in 2016, we get away from that overhead of doing insertions because the Delta row groups are not page compressed. For delete, the problem is that you can have multiple Delta row groups. And those can eat up lots of processing time because you have to search each one looking for the row that you want to delete. So what we do now is we have exponentially increasing size to the Delta row groups. So the first Delta row group may be, where they start out at 16K, 1 meg. So 1 meg, the next one will be 2 meg, the next one will be 4 meg, et cetera. So that drastically reduces the number of Delta row groups that you need to search through in order to find whether you have found your row in the Delta row groups or if you have to go to the column store.
The only comment I'll make is the data row group has 1 million rows, right? When the 1 million rows are done, you go to the next data row group. And what we're doing here is that the first data row group is 1 million rows. The next one that we allocate, we take 2 million rows. So we want to minimize the number of data row groups.
So deal make it here.
Is this on? Okay, now it is on. So the point I was making is the first delta row group has 1 million rows. The next delta row group will have 2 million rows. The next one 4, 8, 16, 32, and then we flat. The goal is to minimize the number of delta row groups so that we don't have to search a large number of delta row groups.
Is that NCCI only?
That is only in NCCI. Yeah.
And as I mentioned, once you have logically deleted a lot of rows out of a column store, there's a bunch of rows that have the notation either in the bitmap or in the delete buffer that this row is logically deleted. So you want to reclaim that space over time. And that's what you can do an alter index reorganize. It's an online operation. Again, it's mostly a space savings operation. So other schemes that we have for minimizing overhead. The overhead is going to hit us the most when the data is already compressed in the row groups. In the Delta store, it pretty much behaves like any other B tree, because that's structurally what it is. So you have an area of the table that is hot and the area of the table that is not so hot. The classic example would be an orders table, classic order entry. So orders go through a lot of changes until they're satisfied and shipped. And at that point, they come pretty static, and you still do analytics on them to find the trends and all that, but they're not going to churn very much. So if we can keep that data in the Delta row group longer, then we're not going to take the hit on the updates that happen to those columns or those rows while they're still in a flux, in a fluid state. So there's a filtered index. So you can apply a filtered predicate to the index that says this index only holds rows where the order state is not shipped, if that's your final end state. So then the column store only holds those rows that don't have that state. The B tree, of course, has all the rows, and the optimizer is smart enough to understand this situation and concatenate the two results. So it'll do the lookup, the scan of the column store index, and then it'll also query the B tree for those rows that don't satisfy the filter predicate. So in that case, you get kind of the best of both worlds, because the data that is static, which is probably the majority of the volume, gets handled very efficiently in the column store. It gets good compression, gets really incredible performance to your analytics queries, and you're not paying much of a penalty for the updates to the data that's still in flux, because it's not in the compressed row groups. In fact, it's not in the column store index at all. But what if you don't have a handy state change that you can do? A filter predicate is a fairly defined thing, but if you know that the records coming into this system will be static after they've been there about 3 weeks, just to pick a date out of the air. So if after some time period it's no longer likely to churn, you'd like to have that kind of a cutoff to what's in your compressed row groups. But since it's not a state change to the data, we can't really trigger off of that. So what we've done is added some syntax for compression delay. So as you define your index, you can give it a compression delay, and that says that any row that has been inserted into the Delta row group, and remember that modifications are a delete and insert, so if it's been modified, it's going to restart the clock for that row version. So anything that hasn't been modified for over the compression delay is subject to get compressed into a compressed row group. Data that's within that window of compression delay will stay in the Delta stores. And again, that's not much different from just another non-clustered index on the system. Also minimizes your index fragmentation because, again, with the column store indexes, it's a delete insert, and you have the logical deletions, which causes logical fragmentation. But if you wait to compress it into those row groups until it's not going to change anymore, then you don't pay that penalty. You're not going to have that fragmentation in the indexes at all. Any questions on all that? Schemes to get around some of the overhead? Yes? So what criteria would you use to choose to add a column store index? So obviously one is, are you doing analytics queries that need to scan huge volumes of data? Yes, reporting sorts of applications where you're... So column store indexes are really good at doing scans, aggregations, sums, those sorts of things across huge volumes of data. They're not real great at doing single row updates. But here you've got the best of both worlds because the B-tree index is really good at single row updates. It's not so great at scanning billions of rows. So we'll use whichever structure fits the query. If you don't have one or the other, then you wouldn't go for the hybrid model.
Question on this compression delay. So, make sure I understand correctly. What you're saying is that with the 30-minute example, every 30 minutes it will compress whatever rows have been added, or is it a 30-minute delay on the individual rows themselves?
So the question is, with the compression delay, does the 30 minutes mean every 30 minutes we'll compress whatever we've got, or does it mean that each individual row has a 30-minute timer? So when we decide to compress the delta row groups into a compressed row group, we will exclude any rows that have been inserted in the last window, so last 30 minutes in this case. So we'll compress everything else and leave off those rows that are still within that window. And row group compression is triggered on the number of rows in the delta row group, or sometimes a time window can trigger it. But again, if you've got compression delay, we will not include the rows within that window.
Does that effectively mean a compression event every 30 minutes on the rows that are eligible?
No.
Or do you still have to have enough to get the rows?
So the question was, does that mean there's a compression event every 30 minutes? That's not what this means. It means that we will exclude, when we do a compression, we will exclude anything that's in that window. It doesn't mean we will trigger every so often.
Okay, and does the row threshold still have to be there? If you had 10 rows, and you only get 10 rows because there's no updates going on, hour after hour after hour.
Right.
Those 10
So
rows are still going to remain in the Delta store.
right. So we're not forcing things to compress every 30 minutes. This is an exclusion, not an inclusion. So we're not forcing it to happen every 30 minutes. We're saying anything that hasn't been around more than 30 minutes won't be compressed. But the other mechanisms are unchanged.
Okay, thank you.
One of the other strategies for minimizing overhead is if you use availability groups, of course, they have readable secondaries. And that's a way to minimize the overhead in memory usage, the contention for memory usage between your OLTP application and your reporting. It's all working on the same table, but now you have a read-only copy sitting out there that you can query against, and the reporting system is typically going to have different data in its memory cache than the OLTP side would, and this way they're not contending for that memory space. And also CPU resources. So now we're going to do a demo. So I set this up in advance. I'm just going to go through what we did to set up the situation that I'm going to do the demo on. So we created a table, orders table, count key, customer name, order number, purchase price, order status, status description, with different values. So it's 1 through 5 for the order status. Created a clustered column store, or clustered index on that table. We set up a loop to insert 3 million rows. In this loop, the order status is all 5, which is the end state. Okay. Now we're going to insert another 200,000 rows where the status is random but not the end state. So we have 3 million rows where it's shipped, which is our end state. And now we have 200,000 rows, which is everything except shipped. Helps if I'm looking at the right database. As expected, we have 3,200,000 rows in the table. look at what the row groups look like. So we have, these are different row groups. You'll see the top one is open, so that's the one that has collected the new rows since the last time we did compression. It has 200,000 rows. The other three are all in the compressed state, so those row groups are fully compressed. The transition to compressed reason is index build. So that's when we built the index after we loaded those all into the table. There's 200,000 rows that are still in the Delta row store, which is what it means when you have an open state. Turn on time statistics and run a query to see how effective that column store is going to be for us. So the point here is how long it took. And we see that the execution time was 97 milliseconds. So not even a second to do that query. Not bad. But there's no comparison there. So let's do a comparison and see what it takes if we tell the optimizer, ignore the clustered column store or non-clustered column store index. So we're explicitly telling the optimizer not to choose that column store index, even though it's sitting there. Probably not something you would do in real life, but so that's almost 10 times longer. It's 3.4 seconds to do that. So that's the gain you get out of scanning lots of data when you've got a column store index. That's the same table, same query. The only difference is which index we told the optimizer to use, either the clustered index or the non-clustered column store.
And that's only 3 million rows. In real life, you may have 1 billion in your enterprise.
That's correct. The comment was that's only 3 million rows. In real life, production analytics, it's not uncommon to see billions of rows, and that effect magnifies. So now there's another table I'm going to set up, which is a filtered index. It shows off the filtered index concept that I was talking about. So we have the same columns. Orders filtered is the table key. Create a clustered index, just like before. Load 3 million rows. All status equals 5, which is shipped. Then we create the non-clustered column store index. And you'll see that it's filtered, and the predicate is where order status equals 5. So only orders that have the status equals 5 will be included in the column store index. All other rows will stay outside of the index entirely, not in the Delta store at all. Now we add an additional 200,000 rows. Again, everything except for the status of shipped. So here we have a query that looks at the count of the rows in the table. So count star as total rows of orders filtered. So everything in that table gets counted. And the second query is the count of those rows where order status equals 5. So we would expect those to be in the clustered column or non-clustered column store index. That's not what I wanted. So we see the difference in the counts there, and difference amounts to 200,000. So this is looking at the row group physical stats, which is taking the physical statistics from the column store index only and extracting out the number of rows. So we're summing up the row groups, total rows, across all the row groups within the column store index. And again, that matches the number of those rows that did not have status equals 5. So indeed, this index does not contain those rows, just like we expected. And again, you don't see those 200 rows in a separate 200,000 rows in a separate row group because they're not in the index at all. You have 3 compressed row groups because they met the criteria, and another row group with 48,000 waiting to be compressed. That all makes sense? And I think I'm going to cut over one other comment I'll make about this demo I've been showing you. The title of the talk is Operational Analytics in SQL Server and Azure SQL Database. And just to show that that was accurate, that demo is running on an Azure SQL Database. So just so you know that this is for real. The way we do development these days, there is one code tree. We drop code into Azure SQL Database about every month. So that is constantly getting refreshed. So by nature, new features turn on in Azure before they land on premise, but they both get the same features. So when you get a release of SQL Server, it'll have the roll-up of everything that people running Azure SQL Database have been using for a while. And that means that it's been shaken out pretty good, because we shake it out really hard before we even let Azure see it. So just a slight commentary on how we do things. So I'm going to talk about real-time analytics with in-memory OLTP. So we've got 2 high-performance features within SQL Server and Azure SQL Database, those being in-memory OLTP and the column stores, in-memory column store. So what if we could put those 2 together? What would that look like? Well, let's see. So again, we're merging both of these, in-memory OLTP plus in-memory data warehousing. 100 times faster analytics speed, 30 times faster OLTP transaction processing speed using the same tables. That's the promise. Let's see if we can deliver. So here we have an in-memory OLTP table. They're not structured like traditional tables. There's no pages in the in-memory system. There's just rows in memory. We do persist them on disk. That's a separate structure. It's not the same as what's in memory, what you see when you're using the database. We have 2 styles of indexes for the operational data. There's traditional range indexes, just like B-trees, like we've always used. It also has hash indexes. Because everything's in memory, we know exactly where each row of data is. And so you define a hash index by the keys, like always, and then a bucket count, which is how many unique, distinct values you expect to see. We run the key values through a hash function, and that gives us an offset into an array of memory pointers that take us directly to the row. So index lookups with a hash index, if it's tuned properly, are order of 1. It doesn't depend on how many rows there are out there. It's the order of 1. So they're really fast. But now we can have an in-memory OLTP table on the same data that is in memory. So a column store index. So the column store index is also kept in memory. We build it in memory as we bring the database online. Actually, we cache the compressed row groups. Have a deleted rows table to track those rows that have been deleted, logically deleted from the memory segments. In-memory OLTP does a similar, create a new version of the row. It's a row version system. So just like column stores, instead of modifying in place, we do a logical delete and an insert. The delta row group in in-memory systems is just a tail onto the in-memory OLTP table. It's not a separate store like the delta row groups. So it's just more data within the in-memory OLTP table that happens to function as the delta row group. You have compression delay option for hot tables, just like on disk. There's a background task that migrates rows from the tail of the in-memory OLTP table into the column store in chunks of about 1 million rows. Column store data is fully resident in memory, which means you're not going to page it in and out as you're working on this data. By the fact that it's an in-memory OLTP table, it means you have enough memory to hold it. Also means the column store is going to run that much faster. It's persisted along with the OLTP data in in-memory optimized file group. Again, no changes to your OLTP application. It just works faster. So let's see what that looks like. Again, I'm going to walk you through the creation step, which I did beforehand. So have a separate database, in-memory OLTP, add the memory optimized data file group and add a container to it. Here we're adding a resource pool to balance the CPU resources used on the operational analytics and the in-memory OLTP queries, so the operational queries and the analytics queries. You can use the resource governor to balance the CPU load between those two. So we're creating a table, same schema as before. Account key, account description, actually a different schema. Account key, account description, account type, units sold. Durability, schema, and data. So if you haven't worked with in-memory OLTP, you have two options. You can make a table schema and data durability, which means we persist everything. It has all the same durability guarantees that any other disk-based table does. We log the data before we return the commit, just like any other time. The log records get harvested and persisted into the memory optimized data store. You also have the option for data that is transient, so the midpoint in the ETL cycle, if you're still using ETL. Session state cache is another canonical example where you can have it durability is schema only. So in that case, the schema is still there, the tables all exist, everything is there, but it's empty when it comes back up. We don't reload the data. So we added an index to the column store, the primary key, again, our clustered column store index with compression delay of 0. So looking at the indexes, we've got a clustered column store index and then a non-clustered hash index on this table. So there's a hash, non-clustered hash index that has all the pointers into the data based on the hash values of the key columns, and then there's a clustered column store index. So again, we inserted 4 million rows in a loop. And indeed, we have 4 million rows in the database. Look at the row groups. So the first one is the name of the table, index ID, row group ID. So all of those are compressed. All 4 million rows are in compressed row group segments. And there's a new open row group to accept new rows that has currently 0 rows in it. So let's look at a comparison of the query performance. So here we're doing an average across all 4 million rows from the table using the column store index. And the elapsed time for that query is 50 milliseconds, doing analytics across 4 million rows. That's good. So what would have been without the column store index? Well, let's see. So again, we have a query hint that says the index is the hash index. And here the elapsed time is 530 milliseconds. So it's about another factor of 10. So between the column store and the non-column store. Pretty nice improvement when you're doing a lot of analytics. So we've talked about what is operational analytics, what are the additional overheads you have to think about when you're setting up one of these systems, and how we've mitigated it within the system, strategies that you can do additionally to mitigate those overheads so it's not a significant drain. We've showed what the benefits are, both what it looks like and what the benefits are for an in-memory system and an on-disk system. At this point, I'm open for questions. Can you put a column store index on a view? No.
Yeah, no, you cannot.
Yes, back there.
Can a table be created on a partition scheme that mixes and matches disk versus in-memory file groups as members of the partition scheme? So that way, if I don't have enough RAM to hold the entire table in memory, part of it can be on disk, part of it can be on RAM.
So can you set up a partition scheme where some of the partitions are in memory and some of the partitions are on disk? You want to take that?
Yeah. So I think it's a very commonly asked scenario. People say, I want to keep my latest partition for in-memory because that's my hot processing going on, and I want to keep my older data in disk-based tables, right? That's a common scenario. The challenge is we don't support that scenario. The short answer is no. The challenge is that concurrency model that we have for in-memory tables is optimistic concurrency control, and the concurrency model for the disk-based table is lock-based. So because of those seams, it doesn't work the right way, and we are working hard to make it happen like that, but it is not supported today.
So a table has to be all disk and all the members.
That's right. So you
Right.
cannot have mix and match.
You can have a separate table and transfer data,
Right.
but that's not a partition switch, which is obviously really efficient.
Right. And I
Also,
think-
partition switches are a logical operation where we just switch the pointers, and these are completely different physical formats. So one way or another, you're moving all of that data between the storage formats.
Right. And I think on the same note, what people have been asking us, actually is a very important point. So for in-memory tables, how many of you went to Yo's session this morning? He had a session, okay, good. So key point is, for in-memory OLTP, all the data in the table must live in memory, right? Now what happens is, you got, say, 100 gigabyte of physical memory, you start inserting rows, and your table size is 8 gigabyte, you say, yeah, it looks good, I'll be fine. But your business grows like crazy, which is good, and you hit 100 gigabyte. Suddenly, your application will die because there is not much memory left. Yes, you can buy more memory and stuff like that. So what people have been asking us, instead of having a hard fall, could you not page in-memory data into disk? I can live with reduced performance, but not my application dying, right? So that is another aspect that we're thinking about. How could we operate in-memory tables when there is not enough memory? So hot, cold partitions and this are very important things for us. We are working through it. We don't have a good solution right now, but we are looking into it. Oh, Kevin? Yes, question. Right. So the question is, like how many of you have heard about read committed snapshot or snapshot isolation, right? Those versions are kept in TempDB, right? The row versioning that we implemented for in-memory tables, those versions are kept in the same database, if you will. There is no TempDB involved. Yeah. Right. That implies even for column store index. In column store index, you are absolutely right. Yeah, it is. Yeah.
Yes?
Slightly off topic, but in a column store index, if you're compressing all the similar values to HD1, how are pointers to the data rows kept in that situation?
So column store indexes, the compressed row groups are inherently not ordered. We do have a row group identifier that we can use as a key into the B trees. So the B tree, that's what the B trees use to locate the rows.
Right. So I think the question is, if I modify a row, how does the pointer is kept? Because everything is compressed, right? So the interesting thing is the compressed row groups are read-only, even for the memory optimized table. Remember Kevin was showing deleted rows table? So when we do an update, we do a delete. So we insert a row into the deleted row. So that's, if you want to think of, that's a version. And then we insert the row. So there is no really a pointer the way you think about in an uncompressed, regular in-memory table.
So basically, it's dropping the row.
You're right, dropping or deleting the row. So the deleted row gets inserted into the deleted rows table, and you can think that as a version. And when we do the query, we need to subtract or filter that row out because that row was deleted, right? Yeah. Good question. Yeah. Anything else? So let me ask you one question myself, because remember we create a clustered column store index on memory optimized table? You saw that syntax? I thought somebody will ask you why clustered column store index. Because clustered column store index is created for analytics. And the interesting thing is, there's a history behind it. But think of a clustered column store index on memory optimized table as a non-clustered index with all the columns. Okay? It's just that the syntax is not there, but it is like a non-clustered index with all the columns. Okay? So think of this, when you do real-time operational analytics, you are creating a non-clustered column store index on your row store table, whether it is a disk-based table or memory optimized table. Right? The syntax is clustered. For memory optimized table, it's a bit confusing, but don't get confused. It is a non-clustered index with all the columns.
So all the rows, all the data is in the memory optimized data area in memory. And it's also all in the clustered column store except for the tail, which is just in the
That's right.
memory.
So second question, I mean, we have done this presentation many times. Second question, people ask us, hey, I'm running out of memory for my memory optimized table, and now you create column store index and you keep that in memory. Will it not take more memory? Of course it will, right? But if you think the column store gives you 10 times compression, so if you were using, say, 60 gigabyte for your memory optimized table, the column store will take 6 gigabyte. That's only 10% more. It's not like a total duplication of the table. So that is an interesting point.
Anything else?
So that means 60 gigabyte table, you move to the OLTP thing, then it's going to come back to 6 GB?
No.
So you have the OLTP table, it's taking up 60 gigabytes. The column store copy of that data is 6 gigabytes again. So if you moved it all into the column store and didn't maintain any other copy, then yes, it would compress from 60 gigabytes down to 6. But here we're saying you need both for your operational store and your analytics. So you have 60 gigabytes for your operational store and an additional 6 for your analytics.
So that's what I was curious about too, and saying that it has no effect on the application. So all this is a copy of your data, or you're applying these indexes directly to your application table?
So think of it as another index, one way or another, because you create indexes to tune the performance in your OLTP application all the time, or your analytics application. This is just another index, and indexes maintain copies of some of the columns. If it's a non-clustered index, you have the non-clustered keys plus any included columns. If it's a clustered index, it's all the columns. Same thing here. If you have, on disk, if you have a clustered column store plus, or if you have a row store that has all the columns and a non-clustered column store index that may or may not have all the rows, then you've got a copy of that much data. In memory, typically you have all the columns in both places.
Right, so I think from application perspective, they just see the same table as before. You just added one more index. And optimizer behind the scene will choose the right index.
Right. So it's relevant in terms of planning resources to make sure you have enough memory, but you don't have to do anything in your application. The optimizer takes care of figuring out what's going to be the fastest way to solve your query.
Okay. So these are the sessions which are related to column store. There is one session that I'm biased towards. It's the customer success stories. So as part of me working on column store, we got many customers who have deployed SQL Server 16 or column store technology on their workload. So we invited them, come here. So one of them is coming from UAE, one is from Europe somewhere, one is from Los Angeles. They're here. They're going to talk about their implementation of column store, both with CCI and with NCCI, what kind of results they got. And I think if you're interested in seeing some real life examples, we saw very small, short demos. I think it'll be very useful. It's on Friday. I really encourage you guys to come. I'm really excited about that. Okay.
Thanks.
Thank you.